Prefix coding is a pretty big deal in the world of compression, but strangely, you don't really hear the words prefix coding in compression circles as often as you'd expect. And one of the reasons for that is that there is this one really important algorithm for prefix coding called Huffman coding. And a lot of times people get so wrapped up in how ubiquitous Huffman coding is that they just say Huffman code when they're talking about prefix codes. This even propagates into documentation for things. So this scheme, deflate, that we are getting dangerously close to talking about in detail. In the documentation for deflate, it talks about how when you compress something with deflate, you need to create a Huffman code. But it turns out actually that if you want to use deflate, you could use any prefix code that meets certain criteria, not necessarily the result of the Huffman coding algorithm. But Huffman coding is so great and so ubiquitous that there's sort of this metonymy effect where people say Huffman code to mean any prefix code. And honestly, even I'm sort of doing that in this lecture because the lecture is called Huffman Coding, but a lot of the stuff in this lecture is just about general prefix coding. It's sort of following on just where the end of the last lecture left off. So to remind ourselves, we're talking about, we've got these sequences of symbols. So I've got this sequence of data S and it's a bunch of symbols. And for the sake of tying in all that information theory stuff from a couple of lectures ago, we can also define a probability distribution based on the observed frequency of each symbol. And then we derived near the end of the last lecture this quantity L bar, the average number of bits per symbol if I use a prefix code where I assign each symbol AI an encoding of length Li. If I do that, the average number of bits per symbol when I encode the sequence S will be this value, L bar. And we also saw that if I come up with a set of code lengths that satisfies a certain inequality, the Kraft-Macmillan inequality, then there will always be a prefix code that has those code lengths. So we actually came up with an algorithm that would generate such a code, which means really all we care about is generating a bunch of code links at this point that satisfy an inequality. And so our question then became, okay, L bar is the average number of bits per symbol if I encode this sequence S. If I can make L bar smaller, then I can make the sequence, the encoded version of the sequence smaller. So anything I can do to reduce L bar results in better compression. There might be other factors in play for a specific application, but in general, as far as getting better compression, what I want to do is reduce L bar. So the question we left off with in the last lecture was, how do I minimize the value of L bar? How do I come up with a set of code links, come up with a prefix code that gives me the minimum possible value of L bar given a particular distribution of probabilities? So here's the example that we were working on a lot in the last lecture. Recall that the first order entropy of this sequence is 3.07 bits. There was this construction we came up with in the service of proving a point that allows us to, for any distribution, derive a set of code links that is viable, that I can use to generate a prefix code. And also recall that this construction, what it's really doing is computing the information content of each symbol and then just taking the ceiling of that, then rounding that value up. Because I want to compare this construction to other things in the next few minutes, I need a name for it. It didn't really have a name in the last lecture. I'm going to call it the ceiling construction, which for lack of any better name should be enough for you to know what I'm talking about. So the ceiling construction gives us a valid set of lengths. It just takes the information content for each symbol and rounds it up. So notice how these symbols with information 3.58 get encodings of length 4. We're lucky for the case of R and B because their information content is a whole number, so rounding it up just leaves it at the same whole number, and they get an encoding exactly equal to, whose length is equal to their information content. But in general, rounding up isn't so bad because we are able to derive a prefix code. And so we can derive this encoding here. That's great. We noticed at the end of the last lecture, though, that there does seem to be room to improve on this. This is a prefix code. It gives us a pretty good result. The result that we were able to demonstrate is with the ceiling construction, you get a value of L bar, the average number of bits per symbol, is less than or equal to the first order entropy, which is the ideal average number of bits per symbol, plus 1 bit. But the thing is, 1 extra bit per symbol is sort of a lot. That could be an increase on this scale, when I'm looking at sequences of length 3, 4, or 5, that could be an increase of maybe 25%, maybe 20%. That's a decent amount. So if I can find any way of driving L bar down further, that would definitely help. Especially if it turns out, as we sort of alluded to last time, but we'll talk about again in about half an hour, if it turns out that conveying a prefix code to my decompressor might be about equally as complicated no matter which prefix code I'm using, then certainly it's almost free to come up with a better prefix code that minimizes L bar. So this particular encoding that we came up with using the ceiling construction, we get an L bar of 3.33. And if you remember that h of s here is 3.07, well then the bound h of s plus 1 is 4.07. So the ceiling construction is actually pretty far away from the bound, from the upper bound according to what we proved in the last lecture. But again, we know that the entropy is 3.07, so there could exist a prefix code with an L bar less than 3.33. Even 3.32 would be better. Any tiny improvement, if I begin encoding sequences, longer than 24 characters, could make a big difference in the long run. So here's the tree representation of that encoding, the one produced by the ceiling construction. And you know from the last lecture that we can take any one of these encoding tables and just draw it as a binary tree to visualize it easily. The case I want to make is that although these links we produced with the ceiling construction are viable, the encoding that we produce isn't necessarily optimal, and there are maybe some obvious ways we can observe that. So notice that there are these two internal nodes that only have one child. So the point of this binary tree representation is to think about differentiating between different symbols in terms of making decisions. If I want to get to the symbol P, I have to go right, then left, then right, then left. And we know that if we represent that in binary, we could call that 1, 0, 1, 0, or something similar. So we could associate bits with directions. So the idea of all these internal nodes is they are a place where I have to make a decision. However, these two internal nodes don't allow me to make any decision at all. I wouldn't stop there because there's no symbol in the middle, and I sort of have to go, in this case I have to go left, and in this case down here I also have to go left. So what's the point? Why do I have this internal node at all? And then I guess you could also consider it from the other direction, which is, hey, wait a minute. The bit strings that could be down here, so all this entire subtree that could exist over here, all these bit strings are not being captured by anybody. Nobody can go down here. There are no symbols in this direction, but that means there's a bunch of room in my encoding that I'm not really taking advantage of. So there's also a symbol that I could put down here, or an entire subtree, but I'm not even using that bit string. This bit string is available. I could add another symbol right now that uses this bit string, but I'm not using it at all. And if there are bit strings that I'm not using, then my encoding probably isn't as efficient as it could be. If I adjust my encoding to capture all possible bit strings, maybe I can do something about L bar. And remember that since L bar is being computed based on the probability of each symbol, which isn't going to change, and the length of each symbol's encoding, if I can find a way to decrease the length of even one symbol's encoding while leaving all else the same, then I will decrease the value of L bar and get a better compressed size overall. So one way of observing this point here, the fact that these two internal nodes are a bit of a problem, without even having to visualize the tree, is to compute the Kraft-Macmillan inequality. And recall from the last lecture that the way that I like to visualize this left-hand side, and just to be clear, the inequality itself, which must be met for any set of code lengths if you want a prefix code to exist, is this. The inequality must always come out to be less than or equal to 1. But in this case, it comes out to be strictly less than 1. So there's actually definitely quite a bit of room between this number and 1. And in the last lecture, I like to justify where I got this left-hand side from as summing up the number of bit strings being captured by each symbol's encoding. Because we know that when we set a particular symbol to have a particular encoding, so if I give R the encoding 0, 0, then every node that could go below this R can no longer exist, because that would violate my prefix-free condition. So all the bit strings that could be down here get captured by the bit sequence 0, 0 being used by R. And I argued that what we're getting on this left-hand side is just summing up all the bit strings that are getting captured. And after a bit of algebraic manipulation, we could view the right-hand side, which boils down to the number 1, but we could write it out in different ways. The right-hand side is almost accounting for all possible bit strings. So one way of thinking of the Kraft-Macmillan inequality is the thing on the left is the sum of all the bit strings being captured by all of our symbols, and the thing on the right is a representation of all of the available bit strings. And so certainly if the number of bit strings being captured is greater than the number available, then I'm in trouble. But in this case, the number of bit strings being captured is definitely less than the number available. So it's less than 1. And that gives rise to a question, which is, why am I not using more of the available bit strings? I've got a bunch of bit strings available, so 16% of them, I guess. Why don't I use all of those? Maybe if I use them, maybe if I capture more bit strings, I can get a better encoding. And so I just need to differentiate two cases here. So in cases where the inequality comes out to less than 1, that means that the number of bit strings captured by all encodings is less than the number available, which means there will be a way to reduce L bar by increasing the length or reducing the length of at least one symbol's encoding. And we'll notice the way we do that basically is we could say, hey, wait a minute, I don't need this node at all. If I move U up in the tree a little bit, if I put it up there, then U's encoding can get shorter, and that means L bar is going to be decreased. And I can actually take this entire subtree and just move it up here as well, and I'll do that in a minute. So in cases where the inequality comes out to less than 1, there is some way to improve L bar. But to be clear, just because the inequality comes out to 1 doesn't mean that my encoding is optimal, because there are other factors that go into an encoding. For example, I could be choosing my lengths in a way that doesn't fairly value each symbol. And so keep that in mind. Just because the encoding equals 1 doesn't mean there isn't a better value of L bar out there. All right, so we had this tree, and we noticed that there were these two internal nodes that don't need to exist. And basically, my logic to try and make this tree better is, if I splice these nodes out completely, then I can reduce the length of some encodings. So basically what I want to do first is, I'll just say, let's get rid of this node and make this subtree here, just make it the right subtree of the node up above. And so I end up with this. And by doing that, I have now decreased the length of the encoding of L, S, and U by 1 bit. And I can do that again because I can say take this U and just move it up there. So this node now contains U, and I no longer have a child. And therefore, the encoding for U decreases by another 1 bit. And that will improve L bar. It has to, because I've decreased the code length of some symbols, but I haven't increased the code length of any other symbols, so I am going to decrease L bar overall. And sure enough, the value of L bar is now 3.17. Previously, it was 3.33, so that is an improvement. And as it turns out, the Kraft-Macmillan inequality now evaluates to exactly 1.0. So I am capturing all available bit strings, as evidenced by the fact that if I look anywhere in this tree, there is nowhere else I can add a leaf without violating the prefix-free condition. Okay, great. So apparently there's no more obvious inefficiency, at least in terms of the number of bit strings that are being captured as measured by this inequality. But the question is, can we do better? I made these sort of weird manual changes. I just dragged nodes around inside of this subtree by inspection. That's already a bit suspicious because it doesn't seem like I'm doing that in a very orderly way. And there's also a question of, wasn't it just sort of blind luck that resulted in these three symbols benefiting? If I'd assigned my symbols in a different order or something, maybe other symbols would have ended up in the subtree that was full of holes. Maybe other symbols could have benefited. It seems like these three symbols getting the benefit was sort of arbitrary. So a lot of this whole process seems a bit ad hoc. What I will observe, I think what alarms me a little bit about the result, is that there now exist a couple of inversions in terms of the value of each symbol, the fair value versus its encoded value. So the symbol U got a lot of benefit from that procedure that I just did. Just by accident, by luck, I was able to move the node for U up by 2 levels. So previously it was encoded in 5 bits. Its information is 4.58, that rounds up to 5, it got 5 bits. After I'm done manipulating the tree, I have an encoding that is 3 bits long. Okay, well, I mean, lucky you, I guess. Now we have a symbol that can be encoded in 3 bits instead of 5. That isn't inherently a problem, except if I go looking at other symbols. So here's a symbol. Let's take a look at let's say the letter P. The letter P didn't change. It previously had information content of 3.58, that rounded up to 4, and it had an encoding of length 4, and it was in the part of the tree that didn't move, so it's still sitting there. I didn't touch it at all in my manipulation. But that means there's now an inversion. Now we've got P, which has an information content of 3.58, being encoded into 4 bits, whereas U, with a larger information content, is encoded in 3 bits. That is not fairly valuing each symbol. I now have a symbol that is worth less being priced higher. And that's a bit of a problem, because the fact that it has less information means it occurs more often. So P occurs twice, as opposed to only once. So I'm going to get more of a benefit by reserving a shorter encoding for P and allowing U to have a longer encoding. So really what I'm saying here is that there are some symbols that are more deserving of that 3-bit encoding than U. So my ad hoc manipulation of the tree wasn't really fair. although it did reduce L bar, it didn't reduce it fairly. Maybe there is an encoding that also gives us this same set of code links, but it rearranges them so that, for example, P ends up with the 3-bit encoding and U ends up with the 4-bit encoding. And maybe you can satisfy yourself that that would produce an improvement if I did that. Now let's consider this tree here, which I generated by some other means. You'll notice that P and Y are in different places. U is not way at the bottom like it was before, but it's a little bit further down than it was in the previous tree. You might also observe this interesting sort of staircase property the tree has that we're going to come back to later. That's not as relevant to the current example. If I take a look at the encoding for this tree, L bar is even lower. 3.17 bit or 3.12 bits instead of the previous 3.17. So I've decreased it by a little bit, but anything helps in this context. And the Kraft-Macmillan inequality again is exactly 1.0, so I'm not wasting any bit strings. I am capturing all possible bit strings. And this new encoding doesn't have any of that unfairness. It doesn't have any inversions between information content and length. Sure, there are going to be cases where the information content of a symbol does not match its length, but there's no situation where a symbol with a low information content gets a longer encoding than a symbol with a higher information content. There still could be ties that have to break one way or the other. So notice that these two symbols do get a different encoding length. So S gets an encoding that's 5 bits long, that would be rounding this number up, whereas U gets an encoding that's 4 bits long, that's rounding this number down. And again, okay, lucky U. However, there's no inversion here because I don't have a case where U is actually worth more than S, but gets a shorter encoding. They're worth the same amount, and so we have to break the tie somehow. And I guess maybe what we could also observe here is by allowing us to break the tie in two different ways, sometimes we round down, sometimes we round up, we don't have the same issue with rounding errors that we might have with the ceiling construction. The problem with the ceiling construction is we're always rounding up. And that means over time we are sort of inflating the average number of bits that we have to use. But rounding up it makes it easier to prove a code exists, which is one of the reasons that we tried that last time. In this encoding, which is a bit more magnanimous, we sometimes round up and sometimes round down. And that hopefully results in a better value of L bar overall. It actually turns out this is going to produce the optimal value of L bar. This tree is one of many different trees that could have been produced by the Huffman coding algorithm on this set of symbols with this distribution. And it's guaranteed if you use Huffman coding, once you have chosen your set of symbols, in this case I've chosen single character symbols, which is what we've been doing so far. Once I've chosen a set of symbols and I know the distribution, and I'm assuming of course that I'm still encoding every symbol separately, so every symbol gets its very own bit sequence. Under that set of conditions, the encoding that's produced by Huffman coding will be optimal. It'll give me an L bar as close as possible to my entropy in all cases. So it produces the minimum value of L bar. And that's one of the reasons we ought to start talking about Huffman coding. So the Huffman coding algorithm takes some information about your set of symbols and the frequency or the probability of each symbol. And which one you use is up to you. It's a matter of convenience, I guess. But the idea is it takes a measurement of the frequency of the symbol where larger numbers mean it occurs more often. So if I have a frequency of 10 or a probability of 0.9, that is obviously larger, the symbol occurs more often than something with the frequency of 1 or a probability of 0.01. That's the idea. So just some measurement that is correlated to, I guess, directly correlated to the number of times the symbol is going to occur. Frequency, probability, whatever. In this lecture, I'm going to mostly use frequency numbers because I feel like for visualizing them, it's a lot easier to visualize things in terms of concrete, discrete frequencies than probabilities, whatever, your mileage may vary. So the way that Huffman coding works, I actually feel like the Huffman coding algorithm itself is pretty intuitive, so you don't need too much, I guess, perspective to see how it works. It's a great algorithm for a second year course, but I think at your level, it's pretty easy to go through an example and talk about it, and I think you'll get the idea. So what's going to happen with my Huffman coding algorithm is it's going to eventually build one big encoding tree. And it's going to do this over a series of iterative merges. It's going to start out with small trees and then merge them together to make larger trees. So at each step, I pick two trees, like let's say these two trees, and I merge them by just adding a new root and joining it to both of the subtrees. And I do this at each step. And the idea is to start with very small trees. And in fact, at the beginning, we begin with single node trees. So a whole forest of trees with one node apiece. And then at each step, I merge two of them together to make one larger tree. And I just keep doing this until there is is only one tree left. So at each step, I'm going to have some set of subtrees, some of these small trees, and they are going to be labeled with their frequency or their probability. So this labeling is the same as in the previous example. So here's U which occurs only once, its frequency is 1. Here's R that occurs 6 times, its frequency is 6. And so the algorithm is going to progress by merging pairs of trees together. So each step is just going to pick 2 trees and then merge them together and then put them back into the collection of trees. And the way that we do this is at each step, we choose 2 trees with the lowest frequency values. So the tree with the lowest and the tree with the second lowest frequency value. In this case, I guess, how about we choose L and S? It makes no difference which 2 you choose if there are a tie. So you'll notice there are actually 3 trees in this case that have the lowest frequency value. So I choose 2 of them, any 2. In this case, suppose I choose L and S. So I pick those 2 trees and then I merge them together into one tree. And I update the frequency value of that new tree to be the sum of the frequencies of the 2 that I merged. Okay, so I have that. At the end of my first iteration, this is what I have. In my second iteration, I pick the 2 trees with the lowest frequency values. And so in this case, it's going to be, I guess, well, the lowest value is 1, and the second lowest is 2, and I've got a lot of choices, but I guess I'll choose the leftmost one. It's the one containing the space. Okay, and so it's an arbitrary choice. I can break the tie however I want. It'll probably come down to what data structures you use to represent this stuff, but I choose these 2, I merge them. Now I've got a tree with frequency 3. Okay, I'll go through one more iteration in more detail, and then we'll sort of skip to the end. Okay, next step, I pick these 2 trees. They both have frequency 2. I merge them together to make a tree with frequency 4. Notice that in this case, A ends up a little bit higher up than L and S because of the way the merge procedure works. Also notice, even early on, it becomes clear that symbols that have a lower frequency tend to be caught up in more merge steps. So U had a very low frequency, and it was merged first. L and S also had low frequencies. They were merged pretty early. And notice how, as time goes by, L has now actually been involved in 2 different merges. And as time goes by, a symbol with low frequency will probably be caught up in lots of different merges because it'll be added to subtrees that are merged over and over again. Because in general, when you have low frequency symbols, they end up in subtrees that are relatively low frequency. And so they're therefore going to become the candidate for a merge pretty quickly in the future. Okay, so we'll do a few more steps here. So we pick these 2 with frequency 2, merge them together. Now we pick 2 with frequency 3 and merge them together. Now the minimum is 4, so we pick 2 trees with frequency 4. We can choose anything we want, but in this case, we'll choose these 2, merge them together. Now we choose a 4 and a 6, and then the 6 and the 8, and then the 14 and the 10, and then we are done. Now we've got only 1 tree left, and so we are done. No more merges are possible. And if you stare at this, you'll observe that although the exact ordering of nodes is different, so if I traverse the tree, obviously the encodings are going to look different, notice that every symbol from our previous example does end up around where we expect it to be. So R, the most frequent symbol, ends up near the top, whereas L and S and U end up near the bottom. They're not all at the exact same level, but they're near the bottom. And in general, if you have a symbol that started with a very low frequency, odds are it got merged pretty early and was caught up in more merges overall. Whereas symbols with high frequencies, we're just going to stay put until relatively late in the process. If we backtrack through it, we'll actually figure out when R finally got merged. Notice that by the time I merge the node containing R, I've already got some pretty complicated trees elsewhere in my data structure. Because R has such high frequency, I wasn't going to touch it until I've already wiped out a lot of those low frequency symbols. And so I guess even in a very intuitive sense, we maybe can see why symbols with high frequency will end up with short encodings because they end up at relatively low depth in my tree. And so one other question we might want to think about is how fast is this? How long does it take to run this algorithm? Because although this might produce an optimal value of L bar, if our alternative, the ceiling construction, produces a value of L bar that's at most 1 bit higher, and this algorithm turns out to be a monster, then maybe I want to use the ceiling construction. But actually it turns out that Huffman coding is pretty efficient. So what I could do if I wanted, and there are a whole ton of ways of implementing Huffman coding, if I'm choosing to use this tree-based representation, because although Huffman coding uses trees, there are lots of ways of representing your tree implicitly, not actually having nodes with left and right children. But if I did that, one way I could run the algorithm is use a priority queue to store each of the trees that I have available at each step, each of my various small trees, and then have the priority queue order its elements by the frequency. And then if I want to do a merge, I just call remove min on my priority queue twice to pull out the two trees with the lowest frequency. I merge them together, I take the resulting tree and I call add to throw it back into my priority queue. And if I do that, then I end up being able to perform Huffman coding in n log n time. As long as I know those frequencies, once I have the frequencies, I can perform Huffman coding in n log n time. And n log n time, as we all know, is pretty good, which means Huffman coding is pretty much the only algorithm I'll ever need to use to generate prefix codes, unless I've got some kind of restrictions in my way. And we'll talk at the end of this lecture about a few restrictions that could get in my way, even in the near future. And then, of course, once I have the tree, I can do what I would usually do with the prefix code. I could then recover an encoding for each symbol by traversing the tree. So in this tree, A ends up being 0, 0, 0, 0, and R ends up being 1, 1. Okay, whatever. There are reasons that we'll talk about in a few minutes that maybe I don't just want to use this encoding. Maybe I want to manipulate the tree a little bit to produce a more predictable looking tree. But in general, once Huffman coding is done, I do have a valid prefix code that gives me the optimal value of L bar. And I mentioned in the last lecture that if all I care about is optimizing L bar, if all I want is a short encoding, then I don't care anything else about, oh, what specific bit sequence did E get? But we're at the point now where maybe we can be a little bit particular about which specific bit sequences each symbol gets. And then if I want to, I guess the slides are being, this is a bit obvious, but yes, I can then compute a symbol table to map each symbol to its encoding. So there's the symbol table I could compute. So to perform encoding, what I probably would do is generate the tree, get a Huffman code, maybe manipulate the tree to get a different looking Huffman code, and then I would compute a symbol table, and then to do the encoding, I just walk through my sequence of inputs and take each symbol, look into the table and grab its encoding and then output that. And so it turns out that the encoding that's produced, regardless of what order I make those merges, as long as I follow the merge rules, it will be optimal. For a given distribution, the encoding of each symbol is as close as possible to the information content of that symbol, but I'm also going to make sure that I satisfy the Kraft-Macmillan inequality. And actually, one thing we can observe is it turns out satisfying the inequality is relatively easy when you think about things from a binary tree point of view. So justifying, I'm not going to try and prove this, but justifying that Huffman coding will always produce something that satisfies the inequality is almost as simple as saying, when you're done, you will actually have a binary tree that satisfies the prefix condition. Because when you think about things with trees, a lot of those other conditions aren't as difficult to, I guess, intuitively understand. In the example we had earlier, where there were nodes with internal nodes with only one child, that's an easy visualization of the case where the inequality comes out to less than 1. In this case, there are no internal nodes with only one child, and every symbol is in a leaf, and therefore it is a prefix code, and therefore we know the inequality is going to be satisfied. Because obviously, to be a prefix code, the inequality has to be satisfied. One thing I'm not talking about, that we're going to talk about a little bit, but that we should be very careful about, maybe we should take these numbers like 75 bits with a grain of salt, is that what I'm showing in the box here is the result of performing an encoding of this sequence using this table. It doesn't account for the overhead involved in telling the decompressor what symbol table I'm using, how I got this prefix code. So obviously that requires overhead, and maybe if I'm not careful, that overhead overwhelms any compression advantage I get out of the actual encoding. So one thing I wanted to swerve over to a different topic quickly, which is, suppose you are the decompressor. And at this point in the course, we're not talking too much about decompression, but suppose you are the decompressor and you've been given the symbol table somehow, and I hand you a sequence of compressed bits. How do you do the decompression? Okay, well, one option would be, here's my sequence of compressed bits. What I could do is almost the brute force option. I could read one bit and say, okay, are there any symbols with a 1-bit encoding? Nope. Okay, so I'll look at 2 bits. I look at 2 bits and say, are there any symbols with a 2-bit encoding? Okay, well, yeah. Is the encoding 1, 1? Yes, it is. Okay, so I guess my first character is R. Okay, so now I look at the next bit. Is there any symbol with a 1-bit encoding? No. Are there any symbols with a 2-bit encoding? Well, yes, but not the encoding 0, 0. Okay, so eat up one more bit. And we can see this is going to be a bit tedious. If I have to keep consulting the table with any number of bits, especially given that I haven't explained how I might implement this table in a way that allows lookups to be fast, this seems a little bit tedious. So the question is, how can I efficiently decompress? Ideally, I want to decompress sort of from left to right. I want to only have to process each bit once. I want to make a little bit of progress with each bit. I don't want to have to keep asking, okay, is 2 bits enough? Is 3 bits enough? Is 4 bits enough? Because that seems like it's going to pile up over time, especially if my encodings end up being a bit longer than in this example. So what I could do is I could reconstruct the tree. And if I have a symbol table, as we saw in the previous lecture, I can always build the tree corresponding to that by just looking at the encoding for each symbol and adding whatever nodes to the tree are needed to realize that path. So in this case, the space goes with 0, 1, 1, 0. Well, that means there has to be a root. I have to be able to turn left from the root, then turn right, then turn right, then turn left. So I just add nodes to do that. And I'll talk about this in a minute, but we can recover the tree pretty quickly. So if I recover the tree, it turns out decompression is pretty fast. I can decompress in time linear in the number of bits, basically. What I do is represent my walk through all the bits from left to right as a walk from root to leaf in my tree. So before I've read the first bit, I start at the root. And then at each step, as I see a bit, I walk around in my tree based on the value of that bit. So the first bit is 1, which means I'm going to walk to the right. Okay, and then I'm stuck here. This is my current state. And then the next bit is also 1, so I walk to the right again. Okay, and now I'm at a leaf. And I know if I've hit a leaf, I'm never going to, there aren't going to be any further steps to make. I've already hit a symbol. That must mean that I'm looking at the encoding for 1, 1, R. So I output the value R, and then I'm ready to start decoding the next symbol. So I just queue back up, I walk back up to the root and start again. And so the next bit is 0, okay, so I walk to the left, then 0, so I walk to the left, then another 0, so I keep walking to the left, and then another 0, so I walk to the left again, and I hit a leaf, and it's A, so I output the A, and I walk back up to the root. And hopefully you can see that because I'm definitely making progress at each step, either I'm hitting a leaf and rewinding and outputting a symbol, or I'm moving within the tree, that I never backtrack, I never have to walk backwards and look at a previous bit again. Hopefully it's clear that this is going to be linear. It's going to be linear in the number of total bits. If you give me n bits, then at each step I pick a direction and walk, or I find a leaf and output a symbol, and that's a constant time operation. So overall, I'm performing a linear amount of work. And then we'll do, I guess, a little bit more here, and then we get to one more symbol. There's the S, and I can rewind, and maybe you can use your imagination for the rest. Here's some pseudocode to model that. So data source here would be some source of compressed bits. You've already built the tree, and you hand me the root. So all I'm doing at each step, I'm asking for one more bit, and when I grab that bit, I am either walking around in my tree, and if I end up at a leaf, I'm rewinding, and I'm just going back up to the root to start again for the next symbol. So this is actually going to be, the formal running time is actually going to be n plus m, because you could argue that when I output a symbol, I'm outputting a certain number of bits, and maybe the number of bits in the output symbol is large or something. So to be really technical, I should also take that into account when I'm considering the running time of this process. But I think still, n plus m is still a form of linear. So this is still a linear time algorithm. I think it's also really elegant. Walking through a tree is a really nice, elegant operation. We can see how we're always making progress. It's true that in practice, when you implement this, like on an actual processor, as you know, when you walk around in trees, if you implement your tree as a linked data structure, when you walk around in those trees, there can be a higher overhead for things like cache performance, so not asymptotic stuff, but practical stuff. It's true that sometimes when you're talking about high performance programming, there are cases where wandering around a linked data structure can cost you a bit in terms of clock cycles. So one other thing I want to talk about is the complexity of actually building the tree. And I did actually talk about this in the last video, but we can build the tree by just walking through the symbol table and just adding whatever nodes are needed for the bit sequence to be realized for each symbol. And that means that the total running time of building the tree, given that adding the nodes themselves, walking through the tree is a linear time operation. To do this walk through a tree and add whatever nodes are needed requires 4 steps. And at each step, adding a node or walking through a node is a constant time operation. So the total running time of actually doing this would be, I guess, just one operation or a constant number of operations per bit in the table. So the total running time would just be the total number of bits in the table, the total number of bits across all encodings. You could also bound that loosely by just saying, look, it's the number of symbols times at most the length of the maximum encoding. So that would be, in this case, 5. So there are, a total of 10 symbols, and each symbol has at most 5 bits. The running time would be at most, 50 operations. There's also this wall of text. You're welcome to pause the video and try and read it. Basically, because in some cases traversing a tree in memory can be a bit difficult from a practical point of view for optimizing things like cache performance, the same reason that often you'd rather use an array than a linked list, there is a way of doing it using a lookup table, although it does require a little bit of finesse. Now, the way that the slide is alluding to here is not the only way of doing it. There are sort of compromises between either using multiple tables or a tree and a table, or several tables in a tree. But in general, using a lookup table is a little bit more complicated than it would be for other types of encodings that we've seen earlier in the course, because of this issue of every encoding potentially using a different number of bits. The slide also observes that although the table-based method might be faster in practice because you're optimizing cache performance better, asymptotically it's the same. I mean, you can't really do better than linear time for decoding a sequence of bits. You have to look at each bit at least once. In practice, though, if you're writing a decompressor that you want to have high performance, you probably would use some sort of table-based method. Just for a very quick illustration of how that kind of table would work, how you use a lookup table, it would sort of have to work like this. So suppose I'm going to use the same encoding that I used in the last lecture, the same prefix code. So suppose I've got A encodes to the value 0, B to 10, C to 110, and D to 111. And you can satisfy yourself that is indeed a prefix code. Suppose also that my compressed sequence is a B, and then a C, and then an A, and then a D. So it's B, C, A, D. The question is, so I can obviously do this by rebuilding the encoding tree and then just using the walking through the tree method we saw a few minutes ago. But how can I do it with a lookup table? Well, basically the idea is, as the previous slide points out, I first figure out the maximum length of any symbol's encoding and then make a lookup table of 2 to that number entries. So I'm going to make a lookup table of 8 indices because the maximum length is 3. Okay, so my indices are going to be 0, 1, 2, 3, 4, 5, 6, and 7. And these are the index. I'm also going to write the index in base 2 because I think that makes it a lot more obvious what I'm really trying to get at here. So the index is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay, so I have this. To make a lookup table that allows me to decode efficiently, I first figure out how many bits are in the maximum length of an encoding, and then I design my decompressor to always work with that number of bits at a time. So since my table is based on 3 bits, what I'm going to do to decompress is always pull in 3 bits of my compressed sequence, and then look up that entire 3-bit sequence in the table. Notice that if I pull in 3 bits, it's not necessarily going to be just one symbol. It could be several symbols, because maybe it's 3 A's in a row, but I always pull in 3 bits because 3 bits is sort of the natural base of my table. And then what I do is I fill my table in based on this encoding table, based on my symbol table, where I use this prefix property, basically the same idea we saw in the previous lecture of capturing bit strings. So here's my index in base 2, and I notice that every encoding beginning with a 0 is going to be an A. So in my table, I fill in every index whose binary encoding begins with the encoding for my symbol with that symbol. So all 4 of the indices 0, 1, 2, 3 will map to A. And similarly, both of the indices 4 and 5 will map to B. And then index 6 maps to C. Index 7, I'm going to rewrite this to be aligned a little bit better. Index 7 maps to D. But I'm not done yet, because obviously if I were to hit a subsequence that begins with, let's do this one here. So I pull in the 3 bits 101. I go to my table at index 101, which is 5, and sure enough, I see a B, which is the first symbol. But the thing is, the first symbol doesn't actually use 3 bits. It only uses 2 bits. And because each symbol could use a different number of bits, my table actually has to contain a bunch of pairs, which is, it tells you the symbol that goes with that encoding, but also how many bits it uses. So A only uses 1 bit, B uses 2 bits, and then C and D actually use 3 bits. All right, and so that way when I go to decode, I first pull in 3 bits at a time, so there's 101. I go to my table, and it says that's a B, but only the first 2 bits are a B. So I decode the B, there's the B, and then I just get rid of my first 2 bits, and then I pull in the next 3 bits. Okay, and so I almost pull in these bits in a sort of queue format. I only expunge the bits from the queue based on what the table tells me to do. So my next symbol is C, so 110. I go into my table at index 110, that's 6, and I pull out, okay, it's C, and it is all 3 bits. So expunge 3 bits, emit a C. Okay, so now 3 bits are gone, and I pull in the next 3 bits. Okay, that would be 0, 1, 1. So I go to my table at index 0, 1, 1, that would be here, and it says that's an A, but only the first bit is an A. So I emit an A, and then I get rid of the first of the 3 bits that I'm working with. And I pull in 3 bits, 1, 1, 1, and I go to my table. And hopefully you can see that this is going to work. It does, however, require a pretty large table, especially if I have a wide variety of encoding lengths. So if some of my encodings have length 10, then to do it this way, the pure table-based way, I would need a table of size 2 to the 10. Now I'll add, as usual in this course, 2 to the 10 is not a large number. I could easily make a table that big. Easily. But that's one reason why when you have massive codes, you have to be a bit careful with this approach, because you can very quickly, because if you have a really weird frequency distribution, Huffman Coding could give you encodings of length 40 or something. You have to be very careful not to assume you can use the table without taking a look at the encoding that you're using, or guaranteeing that the encoding has a certain maximum length, which we'll talk about later in this lecture. Okay, so in any event, now that's enough about decompression. Let's go back and talk more about compression. We do still have to talk about how the compressor sends the encoding to the decompressor. So how does the decompressor know what encoding I'm using? If I provide the decompressor with my symbol table, well, that's great. Then it can decode because it can reconstruct the tree. I guess I could also provide the tree to the decompressor. Anything I can do to give the decompressor my code will allow it to decode my bit sequence. So our question is now, how do I do that efficiently? What is the most efficient way of sending over this prefix code without wasting a huge number of bits on overhead? Well, I could send the symbol table itself, and then the decompressor could rebuild the tree as it sees fit. I could find some clever way of encoding the entire tree. And there are lots of ways of encoding binary trees in clever representations. I could try and leverage one of those. I'm not going to go down that road because I feel like it's almost a moot point. It turns out, based on what we know from experience, so based on what other schemes have done in the past that use prefix codes, there are probably ways we could cut to the chase a lot easier, more efficient ways of doing it. And my observation I'm going to make is, as I've said a few times over the past couple of lectures, I like this encoding because it gives, let's say, R, a low-value symbol, a low length bit sequence, and it gives S, a high value symbol, a longer bit sequence. I don't really care that much what specific sequence S gets. I guess S is getting what, 00011 here? I don't care that much. I wouldn't mind if S got 11010. I don't really care. As long as it gets a sequence of that length, I'm going to get the value of L bar that I want, the optimal value of L bar. So I don't actually need to use this particular code to get the benefits. I just need to use a code with these code lengths. So what I could do is use Huffman Coding to generate this tree, figure out the length of every encoding in this tree, because that's going to minimize the value of L bar, and then come up with any prefix code I want using that set of lengths. So notice that if I were to swap these two nodes here and move R and that subtree over, nothing changes about L bar. Ultimately, the encoding changes, but the compressed size of our data doesn't change at all. And so any other transposition of subtrees is fine. And so arguably, if I were to choose some standard form for my tree, for example, this nice staircase effect here, then maybe I could optimize my encoding of the tree based on the idea that the decompressor already knows the shape of the tree, and therefore I don't have to send as much information. One caveat is maybe there are contexts where I do care about a particular shape of the tree, where maybe it matters that the tree looks like this versus something else. But in most cases, and this is because in practice, Huffman coding or prefix codes are used at the very end of a compression pipeline, there's probably no reason we care that much about that. We just care about getting a particular set of code lengths, usually. And in that context, why not just choose some specific canonical shape of our tree and use that? And the hope, I guess, we have by doing that is that it means we have to send a lot less information about the tree to the decompressor, because the decompressor already knows a lot about our tree. So one option would be to rearrange the tree so that, in a sense, as I go from left to right in an in-order traversal, the depth of leaves is monotonically increasing. And if we agree on a particular shape, then maybe we could just store the depth of each leaf. So I could say this has depth 2, this has depth 3, and 3, and 3, and 3, and so on. And maybe I could just send those links and then send the symbols that go with each link. This maybe sounds familiar because it turns out it is. It turns out that a tree that looks like this staircase pattern, is exactly the tree that would be generated by this algorithm, the algorithm we saw in the previous lecture, the algorithm to create a canonical prefix code based on a set of links that we know satisfies the inequality. And if we do Huffman coding and get some random tree, and then come up with a set of links, and then feed that set of links back into this algorithm, we are going to get a very predictable looking tree shape and a very predictable code. And that means if I choose to do that, I could make sure that the decompressor gets the same tree by making sure in advance that the decompressor has the same algorithm I have, and then just sending it the set of symbols and links, and that's it. So I could send it basically this table, symbol followed by length. And you might stare at this and think, if the length has to be some binary number, why don't I just send the damn encoding? I mean, is that really going to take up any less space to send a binary value of 2 versus this 2-bit encoding? Or, I don't know, like this versus some encoding of the binary value 5? Well, maybe, maybe not. It doesn't seem to be too revolutionary a change. However, one important thing to understand is that the encoding of this table of lengths might benefit from other compression techniques. If I just have a bunch of random bit sequences in here, so I've just come up with some Huffman coding and I've got all these random bit sequences, then maybe that's not so amenable to some sort of extra compression. On the other hand, a table of lengths, where I've sorted the lengths into ascending order, as per the requirement of my algorithm from the last lecture, maybe I can benefit from, I don't know, maybe some RLE or something here, maybe some delta compression when I do these +1s. And so I'm opening the door to use some extra techniques to make this representation smaller. So it turns out that if I were to feed in this exact length table to the algorithm from the previous lecture, I would get this exact tree. And there is some variation that's permitted here because what I'm giving the algorithm is just a set of lengths. I'm not telling it which symbol goes with which length. It just sends me back an encoding that goes with each length. That means when there are ties, if I were to list these in a different order, so let's say in alphabetical order, so B, E, P, Y, then the algorithm would generate the encoding subject to that order, and I would get this would be B, this would be E, this would be P, and this would be Y. And so that's actually a sign that there's a bit more redundancy that I might be able to get rid of, and we'll see a way of getting rid of it when we talk about deflate and bzip. But the idea for now is I've got some vector of symbols and a matching vector of lengths, and I can, if I send over each pair of symbol and length, and the decompressor runs the same algorithm that I run, we can end up with exactly the same tree. And so we could argue this tree, this right-leaning tree, the one that algorithm produces, is an example of a canonical form, because I can rearrange any Huffman tree, or indeed any tree, so any prefix code tree, into this representation without changing the set of code lengths, which is all I really care about. So if I wanted to send this table, I could send it with a bunch of pairs. I could just encode each row of the table as a pair of symbol and length, and I could, I don't know, use 8 bits for the symbol and 8 bits for the length. I could tell the decompressor in advance how long the table is, or I could encode the length of the table into the table itself by, I don't know, using a sentinel approach. If I give a duplicate symbol, the decompressor would see this S and say, wait a minute, I've already seen an S. That doesn't make any sense. You wouldn't need to give me the length for S twice, so I could use it as a way of tipping the decompressor off. This is my way of saying, sorry, the table's over. So I could use a duplicate entry as a way of signaling that my table is over. If I used 8 bits for a length, which for this code would certainly be enough, this would require 21 bytes, which isn't that bad, but it's still 21 bytes. For a tiny input like the one that this one came from, that would be pretty significant. It would, negate a lot of my compression advantage. However, as I mentioned a few minutes ago, the fact that the lengths are in ascending order means that I could benefit from, let's say, delta compression, and then maybe some RLE, as we've done a few lectures ago. So what I could do is encode the first symbol length pair, and then just a bunch of delta values, which I could then benefit from, I don't know, unary encoding or something, to encode in a very small number of bits. So doing that brings us down from 21 bytes down to 13 bytes, which is, I think, pretty good. And it turns out, so bzip uses a combination of delta compression and RLE to store its code length. Deflate uses RLE because there are a lot of runs of the same length or whatever, runs of zeros or runs of other things. But it then uses a separate prefix code. And that sounds a bit weird. Why would it a separate? It's just as weird as it sounds. We'll talk about that more in the deflate lecture. I'll have quite a few things to say about that. But the idea is that large-scale compression schemes have to acknowledge that the actual compression of the data is only one part of the puzzle. When you have all this metadata, when you have to send over the length of your encodings, that itself often requires compression, or else you cancel out whatever advantage you are getting with all of the overhead. So these schemes produce a huge amount of complexity just around things like, how do I compress the overhead for my existing compression techniques? Okay, so a few more examples just to revisit some of the stuff we've seen over the past couple of lectures. So this is an example we've worked with a few times in recent lectures. The entropy is 2.32 bits. If I use the ceiling construction, then I get an encoding that gives me an L bar of 2.7, which isn't as high as it could be, but is definitely notably above entropy. If I use Huffman coding, I get 2.35. And that's a pretty big deal, 2.32 up to 2.35. Keeping in mind that the entropy is this ideal measurement of bits per symbol that doesn't take into account my choice to store each symbol as a separate bit sequence. And if I use a separate bit sequence per symbol, Huffman coding gets me only 0.03 above the entropy. That's pretty good. This string that we've definitely seen before, if I use the ceiling construction, the entropy is 3.49, but ceiling construction gives me an L bar of 4.12. So a pretty decent ways away from the entropy. If I use Huffman coding, 3.51. So entropy was 3.49, and I get 3.51. That's a pretty noticeable difference. Now, especially, I think, given the fact that after all we've discussed about this, sending over the encoding table for the ceiling construction is about as difficult as sending over the Huffman code, because I'm sending over a table like this one way or the other. And so in a sense, that means Huffman coding is sort of free. I get this huge benefit just by running a different algorithm in the compressor. And the algorithm is pretty fast. So Huffman coding is almost a free improvement. And that's one of the reasons when people think of prefix codes, they automatically go to Huffman coding. If I were to try and compress the entirety of A Tale of Two Cities, and one reason I want to talk about that is because, yes, I'm able to compress this to 23 bytes or whatever, but what about the huge overhead of the symbol table, or whatever? There's a bunch of overhead I'm not accounting for here, and these short examples don't really give Huffman coding a chance to shine. So suppose I encode the entire text of A Tale of Two Cities with a Huffman code. And what I mean by that is I'm writing a program that reads in this entire input, and I know that might sound like cheating, but you could argue that it's reasonable for a scheme to read, let's say, 1 megabyte of data at a time. It reads the entire set of input. It then derives a Huffman code based on the frequencies it's observed in the entire input block, and then it compresses it. It compresses the data with that Huffman code. However, this number, which is the total number of bytes I end up with after compression, doesn't include the overhead of storing the symbol table. So it's only the actual bits resulting from the prefix coding itself, not the overhead. Another reason I can justify having an algorithm that reads this entire piece of data before deriving a code is that these three algorithms also do read chunks of data at a time. They're chunks bounded by a constant. That's the important thing. But bzip, for example, at its maximum setting, would read a 900 kilobyte block, which is big enough for this entire thing. So in the interest of leveling the playing field, I think it's fair that I do that as well. As it says, though, we are not including the overhead here. So what about that? These other three schemes are apparently outperforming it, and of course this number is what comes out at the end, which includes all of the overhead. What could the overhead for this be in the case of Huffman coding? Well, let's think about this. So if I use 8-bit symbols, then I guess my symbol table will contain at most 256 entries. Suppose I send my symbol table in the very basic sense of a symbol and length pair, so A and then the number 5. Okay, so what's the maximum length of an encoding? Well, I guess the maximum length of an encoding can't be any more than 256, because in the worst possible case, in the most skewed distribution, the Huffman coding algorithm could produce a tree that's almost sort of a list. but the depth of the tree can be at most the number of symbols. So I think the maximum length of a symbol's encoding is at most 256. So that means I could store the symbol table for this in a very naive way, so not in the most efficient way. I could store it as a set of pairs of 8-bit values, which means to store the entire symbol table, what do I need? Well, I need about 512 bytes. And so even if I factor in the overhead, if I'm even remotely clever, that's only going to be about 512 bytes. And so if I add that onto that, then I get, I don't know, 418K. So 418K versus 753 is pretty good because this is not taking into account things like the redundancies in the text. It's just taking into account the frequency of each symbol, trying to fairly value each character. So, for example, probably giving E a shorter encoding than Z or than punctuation marks. It turns out the entropy of the data, so the entropy of this sequence, if we treat it as an independent sequence of symbols, which I should add it is not, the entropy is 4.39. L bar with Huffman coding is 4.43. So we're right up against that entropy bound. And it turns out if I were to compress to the entropy bound, the lower bound we had for lecture 7 from entropy is 413,000 bytes. So I'm actually pretty close. I'm only 4 or 5K above that lower bound, the entropy bound. Okay, but now that I'm talking about the entropy bound, there's this obvious question. Wait a minute, if this is a lower bound, how am I able to exceed it? How is deflate and bzip and LZMA, how can they go below this lower bound? We spent so much time investing in this idea of a theoretical minimum size of our sequence. How is it that these are just blowing that right out of the water? And the answer is, remember that the lower bound only applies to a sequence of independent and identically distributed symbols. This is not an independent sequence. This original data, an English book, isn't a sequence of independent symbols because there are dependencies. There is the fact that once I see the letter Q, it's pretty likely that I will then see the letter U. The probability that this character is U is different than the probability that this character, the character after the letter T, is U, or in fact, actually even this. If I see the letter U, it's pretty unlikely that the next character is the letter U. Whereas in general, the letter E is very common, but it's pretty unlikely that an E comes after a Q. So there are dependencies between symbols, and as a result, this bound doesn't actually apply. And so these techniques, deflate, bzip, and LZMA, include logic that eliminates dependencies or takes them into account somehow, and that's why they can exceed that entropy bound. But just Huffman coding by itself is able to knock out 300K out of this input. And so we can now see, hopefully, that Huffman coding is a great thing to use just in general. If you have a bunch of symbols, you might as well try as one stage of a compression pipeline employing some entropy coding technique. On the other hand, certainly, maybe before you do that, you want to do whatever you can to create a sequence of symbols that has eliminated as many dependencies as possible. A couple of other, I guess, points off to the side, some of which we'll come back to later. We have covered the sort of basic Huffman coding algorithm, which does minimize the value of L bar. And the basic algorithm just merges subtrees and it breaks ties arbitrarily. In some cases, although this does minimize L bar, the variance of the different code lengths can be higher than you might desire. There is an algorithm that does still minimize L bar, but generates minimum variance Huffman codes. We're not going to need that in this course, but in case you care, or in case you're a grad student that wants to talk about it later, or for some reason if you wanted to use it on, let's say, assignment 4 or something, it's in one of our books. This is a great book for this theoretical style, analysis of compression schemes. So take a look at the book for that. There's also this other thing that I'll come back to in a couple of lectures, which is that some implementations, some compression schemes that use prefix codes enforce a maximum code length. That's for structural reasons. That's often because the number of bits they want to use to store code lengths is limited, and so they enforce that no code can be longer than, the encoding for no symbol can be longer than 16 bits or something. The problem with that is if I have 256 symbols, Huffman coding could make one symbol's encoding 255 or something. And that means if there's a maximum length in play, the basic Huffman coding algorithm could make me codes that are too long. There is a specialized algorithm for limited length Huffman coding, that you give it a maximum length. Like you say, here's a bunch of symbols. I don't want any encoding to be longer than, I don't know, 15 bits. And it will compute the best possible encoding respecting that maximum length. The algorithm that this slide is referring to is called the package merge algorithm, among others. There are a few others that are variants of that. And so deflate has this limit, and if you use the generic Huffman coding algorithm, it could generate a code that doesn't work with the maximum code length enforced by deflate. What's weird is that although there is an algorithm to do this, the basic deflate encoder, the original deflate encoder, the one that most people actually still have the code for, doesn't use the package merge algorithm. And I think the reason for that might be the package merge algorithm came out just before deflate was invented, or maybe during the invention of deflate. So perhaps the author of the deflate algorithm either didn't know or didn't care about the package merge algorithm. And that's why it's not used. Although if on assignment 2 you want an easy way of generating limited length Huffman codes, you should use the package merge algorithm. And so another way of meeting that requirement is you could just generate a tree that is too deep. So if my maximum code length is 3, or let's say my maximum code length is 2, and I end up with some codes of length 3, I could just write an algorithm that manually rearranges my tree a little bit to make it possible to achieve that maximum length. It turns out that gzip, well, the reference encoder, because lots of implementations of gzip exist, but a lot of gzip encoders just do that. They don't bother with a formal limited length Huffman coding algorithm. Instead, they just generate a Huffman code and then try and fix any problems if they arise. Doing so, of course, manipulating our trees manually, as we saw earlier in this lecture, could produce a suboptimal result. But at that point, if all you're doing is you've got some tree and then way down over here, you've got some subtree you're rearranging, odds are all the symbols down here are relatively low frequency, so whatever suboptimalities you introduce by manipulating them aren't really going to affect everything. They're not going to result in too big of an inflation of the total size. So the next lecture, we're going to begin talking the last precursor to talking about deflate. We're going to talk about in the next lecture. And as I said earlier, it's true that a lot of big schemes, deflate, bzip, and LZMA, do use entropy coding, but it's pretty obvious they're doing something else. And what's interesting is deflate and bzip and LZMA don't do that much else. The bzip and LZMA do a decent amount of other stuff, but not that much of other stuff besides creating a stream of symbols that is then optimized for good entropy coding. Deflate, in a very strange backwards sense, is almost pretty simple. Deflate has pretty much two major steps, which is first, a particular scheme called LZSS, which we'll talk about in the next lecture, gets used to eliminate redundancies, to eliminate recurring macroscopic patterns in the data. And then the resulting sequence of symbols, which is a symbol set that is different from the symbols that came in, that is subjected to Huffman coding. That's really it. In a macroscopic sense, deflate is just these two algorithms in this order. As we'll see in a couple of lectures, in a microscopic sense, deflate is hideously complicated because besides having to just do these two things, it also has to optimize away a lot of the overhead of explaining to the decompressor how it eliminated the patterns and giving the decompressor some idea of what Huffman code it used. And so strangely, although the underlying architecture of deflate is based on two simple things, deflate itself is full of all these weird tricks to squeeze just one bit out of headers or out of overhead to try and optimize compression. So in the next lecture, we're going to talk about Lempel-Ziv schemes, including LZSS. You're already familiar with LZW, that's one member of that family. And then, once that lecture is over, we're going to talk about the nuts and bolts of the deflate scheme at a very low level.